This is a 10-part series of fundamentals of X-ray diffraction. At the beginning, I would like to show the contents of each part. In Chapter 1, the properties of X-rays are explained. In Chapter 2, I'll explain the generation of X-rays including white and characteristic radiation, which are used in normal X-ray diffraction experiments. The topic of Chapter 3 is interaction of X-rays with matter. X-ray absorption, fluorescent X-rays and scattering X-rays will be explained. Chapter 4 is about the geometry of crystals, and how to determine Miller indices and direction indices. In Chapter 5, I'll describe X-ray powder diffractometry and its applications. Then I'll introduce the X-ray diffractometer in Chapter 6. Next I'll explain the focusing method based on the Bragg-Brentano geometry in Chapter 7. The parallel beam method will be explained in Chapter 8. And next diffraction angle errors related to the goniometer method will be explained in Chapter 9. Finally, I would like to introduce some precautions of handling X-ray diffractometer in Chapter 10. Before starting the main topics, let me explain briefly why X-rays are used for the crystal structure analysis. We can see colors and shapes of an object by visible light in the region of several thousand angstroms with our eyes. But we cannot see the arrangement of atoms at several angstroms of separation. Using X-rays having wavelengths around 1 angstrom which are very close to interatomic distance, we can get the information of the crystal structure of the object. The very important point is that the wavelength of X-rays used for any crystal structure analysis is very close to the distance among atoms. The topic of Chapter 1 is the properties of X-rays, which is closely related to what X-rays are. X-rays were discovered in 1895 by the German physicist Röntgen, and were named so because their nature was unknown at the time. Unlike ordinary light, these rays were invisible, but they traveled in straight lines and exposed photographic film in the same way as visible light does. And also it was revealed that X-rays penetrate a human body and metals depending on the thickness, and that X-rays induce fluorescent X-rays, and some other properties. As soon as his report was published, it was rapidly accepted by the people due to his fame in the field of physics, and because it was associated with easily understandable results such as X-ray photographs, which were soon started to be used in medical treatments. Because of this achievement, he was awarded the first Nobel Prize in Physics in 1901. X-rays discovered like this were subsequently revealed to be electromagnetic waves, having exactly the same nature as that of visible light, but having much shorter wavelength. The electromagnetic waves can be considered as a wave motion in accordance with classical theory. Simultaneously, electromagnetic waves can also be considered as a stream of particles called photons according to quantum theory. I'll explain the wave-particle dual nature of X-rays. We use sometimes one nature and sometimes the other to explain various phenomena, giving a preference in general to the classical theory whenever it is applicable. At first, I briefly introduce electromagnetic waves. An electromagnetic wave is the form of energy emitted and absorbed by charged particles, which exhibit wave-like behavior as it travels through space. It has both electric and magnetic field components. which stand in a fixed ratio of intensity to each other, and which oscillate in phase perpendicular to each other and perpendicular to the direction of energy and wave propagation. And this periodic wave is called a wavelength, conventionally denoted as lambda. Behavior of the electromagnetic waves differs significantly depending on the wavelength. I introduce the types of the electromagnetic waves, and their usage simply the next slide. The 9 types of the electromagnetic waves are shown from shorter to longer wavelengths. The wavelengths, longer than visible light, are generally used for radios, TVs, microwave ovens, communication devices, heating appliances and some other applications. Visible light has the wavelengths we can see with our eyes, such as a rainbow after rain, or the spectrum of sunlight dispersed by a prism. The wavelengths just shorter than visible light correspond to ultraviolet rays, used for the treatment of skin diseases, or ultraviolet lamps for disinfection and some other purposes. We know that excessive sunburn by the ultraviolet rays lead to the high risk of skin cancer. The range of the wavelengths is shorter than the ultraviolet rays corresponds to X-rays. Soft X-rays having relatively longer wavelength are used for surface analysis, and hard X-rays having relatively shorter wavelength are used for X-ray machines in the medical front, and for X-ray diffraction analysis in industry and academia. The shortest wavelengths correspond to gamma rays. And then, the range from a part of the ultraviolet to the gamma rays is called ionizing radiation. When we use it, we have to follow the law, such as Ordinance on the Prevention of Ionizing Radiation Hazards in Japan. Generally, a lot of people don't know exactly what X-rays are, despite X-rays being used frequently in our daily life. And also they may think that X-rays are very dangerous, the same as other radiations. The information I'll describe from now is not deeply related to X-ray diffractometry, but I think it's a good chance to show you the differences between the X-rays and other radiations, through the generation mechanism and penetration force of the ionization radiations. Are you aware of the dotted red diagonal line between the hard X-rays and the gamma rays different from other lines? It has a meaning. In the range of the wavelengths between the hard X-rays and the gamma rays, sometimes it's called X-rays or sometimes it's called gamma rays due to the generation mechanism, even though they have an identical wavelength. Let me explain the difference of the generation mechanism between the hard X-rays and gamma rays. X-rays are electrically generated by the impact of electrons coming from a filament and colliding with the target metal. On the other hand, the gamma rays are generated from nuclear reactions such as alpha decay or beta decay. I show very simple explanations of alpha and beta decay. For example, the gamma rays are emitted in alpha decay of heavy nuclear like uranium fission. 2 protons and neutrons called alpha particles are discharged, and then changes to a lighter nuclei and a nuclei of helium. The gamma rays are emitted as surplus energy at the time. In the beta decay, the gamma rays are also emitted. This is an example of the radioisotope nitrogen-16. When it becomes an unstable state due to the emission of an electron, it tries to recover a stable state again by emitting the gamma rays, and then it changes to the stable isotope oxygen-16. The particles such as the alpha, beta, neutron rays and the electromagnetic waves like the gamma rays, X-rays, and others are called ionizing radiation. The alpha rays can be stopped by a piece of paper. The alpha particles consist of 2 protons, and 2 neutrons unites together into a particle identical to the helium nucleus produced in the process of alpha decay. The beta particles are high-energy, high-speed electrons or positrons, and stopped by a few millimeters of aluminum. The true nature of the X-rays and the gamma rays is the electromagnetic waves. They can be stopped by a lead plate or thick metal plate. That's why an X-ray diffractometer has very thick iron radiation enclosures. Neutron particles can be stopped by a thick layer of water or concrete. A neutron particle has high penetration power because of no charge. It is a wonder how the thick layer of water can stop neutron rays which cannot be stopped by the lead plate, isn't it? That is because speed of a neutron particle decreases by half, due to only one collision with a hydrogen atom in water, because it has the same mass as neutron particle does. The mechanism of X-ray generation is completely different from those of the alpha, beta, gamma and neutron rays. Some people who work at X-ray laboratories worry about using X-rays without appropriate knowledge on X-rays. As long as we can correctly control the electrical generation and usage of X-rays, we can use them safely and easily. I got off the track a little bit, and explained that X-rays are the electromagnetic waves. Now I explain a dual-wave particle character. The electromagnetic waves can be considered as a wave motion in accordance with classical theory, and as a particle called photon according to quantum theory. The wave motion shows the diffraction phenomena, and each photon is associated with an amount of energy inversely proportional to the wavelength. Let me explain the wave motion first. When you throw 2 stones into a pond, you can see 2 wave patterns on the surface. And then the 2 wave patterns interfere and finally they spread out in a large wave pattern. This is called in phase. In the case of in phase, it gives a strong effect to make a large pattern. In the case of out of phase, the waves are cancelled out each other. The same wave interference occurs with X-rays too. When X-ray wavelengths are in phase like the wave interference of water, the diffraction phenomenon is exhibited. And X-rays also behave as particles. Therefore they can be counted 1, 2, 3 and etc. The energy of the particle is calculated by dividing 12.4 with lambda. 12.4 is Planck's constant multiplied by the speed of light. The formula shows the relationship between a wave and a particle. Long wavelength has low energy, and short wavelength has high energy. Finally, let me show you an imagination of the dual wave particle nature. X-ray photons can be counted and each photon oscillates with the wavelengths. X-rays interact with matter and show some properties. I explained 5 properties by the interactions of X-rays with matter. X-rays expose photographic films. You have seen X-ray photographs, for example in your medical checks. This is an X-ray photograph of a mineral sample. The next property is fluorescent behavior. X-rays produce fluorescence when they strike on particular substances such as zinc sulfide, cadmium sulfide, and sodium iodide and others. This property is used to detect X-rays in an X-ray diffractometer. The main detector using fluorescent behavior is a scintillation counter. The typical detector using fluorescent behavior is a scintillation counter. As an X-ray photon hits the scintillator NaI, sodium iodide, fluorescence is produced proportional to the energy of the X-ray photon. The scintillation counter counts the number of X-ray photons translated electrical pulses, which correspond to the intensity of fluorescence. There is an imaging plate except the scintillation counter. The next property is ionization behavior. When an X-ray gets into matter or gas, it ionizes atoms and generates a negative and a positive ion. And it is also used for a detector of X-ray diffractometer. This is a schematic illustration of an atom. There are a lot of orbits around a nucleus, and each orbit has a certain number of orbital electrons. As an X-ray photon hits an outer orbital electron, it kicks the orbital electron out of the atom. Due to this, the atom becomes a positive ion, making an ion pair with the electron kicked out from the atom. One detector that uses this ionization process is a PSPC, position-sensitive proportional counter. The refractive index of X-rays is nearly equal to 1. Therefore, X-rays cannot be focused by refraction. Visible light refracts at the interface of materials different in density. This is why a straight bar seems to be bent at the interface between air and water. In contrast, X-rays travel straight without refraction even at the interface of the two materials different in density. And when X-rays hit a smooth surface at a very shallow angle, they do not go into the material, but instead most of them reflect off the surface. This phenomenon is called total reflection. The last property is the penetrating power of X-rays. X-ray penetration power is used for medical checks by X-ray imaging machines, and for non-destructive testing in industry. Here let me introduce some Rigaku products for X-ray non-destructive testing. There are mainly 3 types of machines for X-ray non-destructive testing: portable industrial X-ray inspection apparatus, high-resolution 3D X-ray microscope, and 3D micro X-ray CT for laboratory animals. Portable industrial X-ray inspection apparatus can be used to find defects inside of buildings, bridges, tunnels, oil and gas pipes and other structures. The high-resolution 3D X-ray microscope may be used to check PCBs in products of the apparel industry and others. "3D micro X-ray CT for laboratory animals" is the apparatus for experimental animals. Given these properties are used for X-ray powder diffractometry and X-ray non-destructive testing, which is contributing to development for scientific fields.